what we talked about the last time and what you did a lot in recitation is how to do math and how to build that ALU. And I saw from the notes that were on the board here that you even went into how to multiply, which is really good because you got to see a little bit sort of more advanced stuff that would go on in an ALU. So again, since we're sort of doing this kind of top-down from the block diagram down to the individual pieces, we're going to take a look at another one of the pieces inside of our system. And in particular, today we're going to look at the memory. And if you remember, inside of this system here, there were really kind of three kinds of devices. There was the computation of the ALU, and we did that in the last class. And there were these multiplexers, which I explained to you how those things work, right? They were a thing that either chose this input or that input. But there were also these memory systems, and in particular there were the write ports to the register file, to the big slow memory over here, and to the program counter. And then there were a whole bunch of read ports, both to the big slow memory over here, and also to the register file over here, and also from the program counter over here. Okay, so today we're going to concentrate on the memories. So it's really how do we build those particular things. Well, let's first of all take a look at a basic element, and I introduced this when we introduced the system as a whole, but I want to kind of do it again, and this is the enable controlled register. This is that thing that works just like the camera that we talked about before, where there is a shutter. That's the clock over here that when you press, you have a rising edge going from 0 to 1 on the clock over here. This device takes a picture of whatever the inputs are on D here and propagates the value to Q, and most importantly holds on to those values for the remaining of the clock cycle until once again the shutter is pressed. Furthermore, if the shutter is pressed and the camera is turned off, in other words, the enable input over here has a 0 on it and not a 1, then it will ignore the clock input over here, and the Q output will continue to hold on to the data that it had before the clock went from low to high. Okay, everybody remember that? And that's basically how that unit worked. This is a 32-bit version of the thing, which is a 32-bit register with 32 bits of D and 32 bits of Q.
If the enable is on, then it empties itself?
It's not that it empties itself, but that when the clock goes from low to high, a short time afterwards, Q takes on what D was when the clock went from low to high, and then Q holds on to whatever that was until the clock goes from low to high again when the enable is also on. So it's really kind of a camera where the film just sort of freezes whatever was in front of the lens when the shutter was pressed and holds on to it till the next time that you press the shutter.
So there's always an image until it's written over.
And until it's written over. There's always an image until you write over it. Okay? But keep in mind that the enable allows you to sort of turn the camera off and prevent the shutter from having any action. And the shutter in this case is the clock. And so this is going to be the basic element of memory.
So what value does D have then? When Q takes on the value of D and then D?
Well, D can, after the snapshot is taken, what's in front of the lens can change however you want.
Okay.
And so we don't specify what D is, except that when the clock goes off, whatever D is, Q takes a hold of that and latches onto it for some time. Okay? We're actually going to be talking in future classes about how to build those things. And you're going to learn from a circuit perspective actually how to build a circuit to function as the camera that you see here. And it's lots of fun. Okay? And we're also going to learn about what happens when the person in front of the lens is moving when the shutter is tripped. You know, film never does that, but when everybody else takes a picture, half the time the people are moving, right? And you get this blur. Well, it turns out the same thing can happen here, and we're going to learn about how to deal with that. But for now, let's not worry about that issue, and let's assume that all of the data inputs, stand still to get the picture taken. Well, we have this register file. And the register file, if you remember, had 32 registers in it, of which the last one is going to be all 0. So there's really only 31 of them. So I could take 31 of these 32-bit registers over here, and I could arrange them in a row, and I could say, okay, this one over here is going to be R0, and this one's going to be R1, and the next one down here, R2, R3, all the way down to R30. And if you remember, R30 and R29 and R28 were special ones that we're going to use for special purposes, like the stack pointer and the linkage pointer and stuff like that, basic frame pointer and the exception pointer. That doesn't matter. We still have 31 registers. And then this last funny one, which is all 0 all the time. And the question is, if we have these building blocks, each of which acts as a camera, so now we have 31 cameras arranged all in this column here, how do we build a system to select which one of those I want to read on any given cycle? Because again, I'll go back to the architecture here, and if you remember, the way that this worked here is that we had a 5-bit address that came in here on RA1, and that selected one of the 32 registers, right? And the results of whichever register it picked were supposed to come out here on RD1. And similarly, this was another port into the same register file that selected one of the same 32 registers that this thing here looked at, and whichever one it chose was supposed to come out here on RD2. And so the first question that comes to mind is, if I'm going to build this thing out of 32 units which look kind of like this thing down at the bottom, or excuse me, I should say kind of like the program counter here, where there's just a 32-bit number held in one thing, if I'm going to build it out of those, how do I choose which of the 32 gets read by any one of those read ports? And the answer is actually very simple, and you've already seen the part which allows you to do this. It's called a selector or a multiplexer. And into the control input of the selector come 5 bits. And they specify one of 32 possible combinations. And those combinations each stand for selecting as a data item to be steered to this output, RD1, one of the 32 possible registers. Okay, if you remember the selectors we used before to steer how the data moved one way or the other inside of the circuit, this is the same thing. If we wanted R0, we would put a 0 into here, and the selector would choose, we'd draw a red line between here and here, saying that we're going to choose the output of this guy up here, all 32 bits of it, to get steered down to here and come out. On the other hand, if we put a 1 into here, we're going to choose this one. A 2, we'll choose this one, 3, 4, 5, 6, 7, all the way down to register 30 down here. And if we choose register 31, which is the last one of all, what do we get? We don't get the output of one of these registers, we get the output of this wire, which we tie all 32 bits to 0. And thus we've built ourselves a read port for a 31 register file where the 32nd register is always read as 0. And so this is the method that we're going to use to create access to these different registers. Make sense? We're just going to use a selector to do the whole thing. And later on, we're going to talk about how to build one of these. Okay, how do we add another port to this thing? Easy. Put in another selector. So over here on the right, we have the selector for RD2. And so into this input over here comes RA2, the second address that we're trying to look at. Notice that there's only one set of registers, but there are 2 different ports for accessing them, 2 different views looking into the register file, and we get to examine 2 different registers simultaneously, one being chosen as RA1 over here on the left, and another one being chosen as RA2 over here. And for instance, this one could be choosing R0 to get steered to the output here, while this one over here chooses R1 to be steered to the output here, and each one would get a different piece of data from different registers that are over here on the left. Is this clear? Are there any questions about the sort of trick that we're doing here? Yeah?
Can you put in any value in each?
You absolutely can. There's nothing wrong with saying, I want to add the contents of R0 to the contents of R0 and put the result into, let's say, R1. Okay, it turns out you can also put the result into R0 as well, and we need to talk about what happens when things go around in a loop. But for now, let's not worry about that and just say, sure, there's nothing wrong with putting the same number in here as the same number in there, and you know that both of these selectors will select the same thing, and you'll get the same data out of both of them. Okay, so this is a 2-read port register file. Yeah,
Could you just remind me what RA and RD stand for?
sure. RA is read address and RD is read data. Okay, we're also going to have WA and WD for write address and write data. So that's how we read from these registers. Now, I haven't talked at all about how we get data into them yet. But guess what? There's some blank space on the left side of this picture. And through the magic of PowerPoint, we're going to fill it in. Okay, how do we write selectively? Now, obviously, if I wanted to do this the dumb way, I could hook all the D's up to the same set of wires, and I could turn all the E's on, and in one swoop, when those clocks went off, I could write all of the registers at the same time. Or I could say the way that I'm going to control which one gets written is I'm only going to snap one of the shutters at any given time. In other words, I could gate the clocks. I could put a bunch of AND gates with the clocks, saying depending on which of the registers I wanted to write, I'm either going to trigger this clock or trigger this clock or trigger this clock. Change which shutter gets the finger to press on it. But it turns out, and we'll see reasons later for why this is true, that trying to gate clocks, trying to control which shutter is pressed, is actually very hard to do. And it's actually easier, and you get much more time to get the job done, to disable certain of the cameras and only enable one of them so that all the shutters are pressed at the same time, but only one of them works. And let's take a look at how that works. What we're going to do is we're going to take the data input of all of the registers, and we're going to hook them together in parallel. And we're going to call that the write data input to the register file, WD over here. So whenever we want to write the register file, we're going to give it 2 pieces of information. One is going to be what data we want to write in, and the other is which register we want to write it to. The data goes into WD over here, and the address, which of the 32 registers we want to write, is going to come in here into this place called WA for write address. And that's going to go into this thing. And this device over here looks just like this one over here, except this is a selector, and this is kind of the mirror image of that. And guess what this is called? This is called a decoder. Okay, and what it does is it decodes an input here, which is 5 bits wide, and it figures out which combination of 5 bits those are, of the 32 possible combinations there are. And if the combination is 0, it steers this signal over here up to 0, in the same way that if RA1 is 0, it steered the 0 over here all the way down to here. So it kind of works the same way, but backwards. Okay? It takes a small number of inputs and chooses amongst a larger number of outputs. And so it will steer this input, write enable register file, or WRF, to one of the enables on the registers. Now the question remains, what is going to be the E of all of the remaining ones? And what do you think the answer is? 0, right. So the way that these decoders work is that they set everything to 0 except for one of the outputs, and that output is set equal to whatever this data input is here. And in particular, this says whether or not the register file as a whole should do the write. And what that really means is, let's say we're writing to register number 0, and this wire is connected up to the 0 up here. It's saying, should register 0 pay attention to the data that comes in here when the clock goes off? And if WRF is 1, then the answer is yes. And if WRF is 0, then the answer is no.
So
it will not write
something.
something.
Just 1 bit.
It's just 1 bit, either 0 or 1. Okay, so that's the general idea. Hey, look at what happened to register number 31. If we choose to write register 31, all the rest of them are going to be 0. And register 31, this little wire is going to come out here and say, poor, pitiful me, no one's listening to me. And why is that? Because the bits that come in here on WD just go nowhere. And so none of the registers is going to be turned on if we choose register 31 as the write address destination for where we're trying to write. And that's how we implement in this very trivial way, making register 31 equal to 0 on read and ignored on write. That's all there is to it. Okay?
So looking at it, it looks natural, perhaps if you were writing to several registers at the same time, but you don't do that.
Well, but we actually don't, right. It looks like we're trying to do it. It seems like we're trying to write to all the registers at the same
No,
time.
no, no, I'm saying, in our implementation, you always choose one. Right?
You only choose one.
Why not choose more? That
Oh,
might be
okay.
efficient in some cases.
It may be more efficient. Perhaps we could have special opcodes that wrote to 2 registers or to 3 of them. In that case, we would need to design this thing differently. You're absolutely right. Part of the idea here is to minimize the number of wires that are going to control the box here. So in other words, we need 5 bits to specify 1 register to write to. If we had 2 registers to write to, we'd need 5 bits for one of them and another 5 bits for a second one. And so you may, for instance, want to set it up so that we can write to more than 1 register. Okay, or we'd need a separate one of these E lines for each of the registers, so maybe we'd want to write to more than 1. But most programs and the instruction set architecture that we've designed is one that really only writes to 1 destination at any given time. The opcodes are always operate on RA, RB, putting the result into RC. So there's really no even mechanism for saying I want to write more than 1 register at any given time. But you're right, you could design this in a different way, where you did not use a device like this, but instead had 31 separate wires, of which more than one of them could be on, for instance, to turn more of those on. Yeah,
You said the worth is only 1 bit, 1 or 0, right?
that's correct.
But why would it ever be 0? Because then that would mean that even the address of it specified won't be enabled.
That's absolutely right. But we did see some instructions in the, not the last class, but the one before. For instance, a store instruction or a load instruction where we did not want to write the register file. So sometimes we want the machine to do something that does not involve writing to a register at all. And in that case, we make WRF equal to 0.
What end effect would that have of specifying an address, specifying data to be written to it?
Then nothing happens here.
Okay.
Okay? But often that address is used for some other reason. Okay? So if you kind of go through the different opcodes that we went through, you'll see that in some of the cases, WRF was set to 0. And in those cases, the idea is that the register file is told, don't write.
How is that different from having the work be 1 on the register?
It's exactly the same. But sometimes we're using the bits for register C for some other reason. And so I think that you'll find when you look at the code that there's some of those cases where we want WRF to, in fact, be 0 because we're using those bits for some other thing. Okay?
When these lines are 0, is that just lack of signal, or is there a signal that indicates 0?
So I've brushed all that stuff under the carpet for now because we're doing this kind of top-down view of things. But very soon we're going to take a look at how different voltages are used to represent 0s and 1s. And there's actually a choice that we have whether we want a low voltage to represent a 0 and a high voltage to represent a 1, or do it the other way around. But I can assure you that we do it one way or the other. Okay, that we're going to make a choice in each part of the system what the representation is between voltages and a logic 0 and a logic 1. So typically, if you wanted to do it in most cases, something that's near ground, near 0 volts, is going to be a logic 0. And something that's a higher voltage, perhaps 2 volts, perhaps 3 volts, perhaps 5 volts, is going to be a logic 1. And we'll talk a lot about the specifics of how that mapping is done. But for now, I'd like to think of these just in terms of the symbols 0 and 1. And we'll get into exactly how to implement those a little bit later. Okay. So we need to understand how this thing works, this decoder. It's also called a demultiplexer, the same way the other one is called a multiplexer. And I basically told you how it worked, how it took an input and sort of chose the different outputs. Turns out you could implement this a slightly different way. And there were computers like the, I know the PDP-11 did this, I think the VAX did this too. This was a standard trick, I think DEC even had a patent on this, for how to lower the number of wires that crisscross across the register file. Now, in order to grasp why this picture is important, let's back up a second and look at the previous picture. You'll notice in the previous picture, I have 32 bits coming out of each of these registers. 32 plus 32 plus 32 plus 32. I have 31 copies of 32 bits, which is many, many bits. And they go to this multiplexer right here to select one of them. and then the output comes out here. A typical register file back in the 1970s, 1980s was built as a single chip with this multiplexer and the registers all inside of one integrated circuit. Okay? And the question was, if you had such a thing and you wanted to add another read port to it, how could you do it? And the answer was it became too difficult to do because there were so many wires that crisscrossed across the entire chip that it became very, very hard. So a neat little trick, which I want to show you, and I think you'll like, which they came up with in those days, and it doesn't matter quite so much now that integrated circuits are so much more dense, is the following trade-off. And this is kind of indicative of all kinds of trade-offs that you can make between complexity and cost. Instead of having the same bits from all of these registers go to two multiplexers, what architects in those days did is that they duplicated the register file twice. In other words, this register file over here on the right is exactly the same as this register file over here on the left. Each of the register files has one write port, just like we had before, and only one read port. And this register file here also has one write port and only one read port. Now this is small enough that we can fit this entire thing on a single chip. And the thing on the left being exactly the same as a second chip. And now when we look at the two halves, how do we keep the two registers in sync with each other? Well, the answer is that whatever we write into the left one, we write also into the right one in parallel. In other words, the address that we choose to write at any given time is sent to the left decoder here and sent to the right decoder at the same time. So whenever we write a register on the left, we write the same register on the right. The same data that we send to the left is also sent over to the right. So the data is the same. So you know after a while, after you've written the left file for a while, you've written the right file for a while, assuming you've hit all of the registers, what's going to be the case? The contents of the ones on the left and the contents of the ones on the right are going to be the same. And that means that when you access the read port of the left-hand file, you could also access a different register using the read port on the right-hand file, and it would work exactly the same as that other system I just showed you, where we sort of had a single set of storage and had the wires bust across two different selectors for the two different ports. So this is how to build a two-port register file out of two one-port register files. And the answer is to just sync them up so they both have the same thing on them. Okay, it's kind of a cute trick. And in particular, it turns out that the circuitry involved in building this, guess which takes more circuitry? To store the bits or to select the bits? Now, you'd obviously think, oh my God, trying to remember, building a camera is a hard thing, right? But actually building the selector is harder. Okay, this is this big tree structure that says, okay, if it's one of these two bits, we choose these, then we choose these, we choose these. You get this huge tree here, and this one actually takes up most of the transistors on the chip, and this takes up very, very little. Okay, and the wires take up a lot of space too. And so it's actually sometimes more economical to build a structure that looks like this because it turns out that storage is cheap. Storing bits is cheap. However, conveying bits is difficult. And in particular, choosing which bit you want to look at is a little bit more hard to do. So anyway, I just wanted to show this to you because it was both a neat bit of history, and if you understood how this worked, you would know how the system worked as a whole. Okay, what do we do with the clocks? All of those different registers that are in the middle here each have a trigger on them, a shutter at the bottom, and the question is what should we do with all those clocks? So what is the answer? There's some single clock that's going to come into this thing that says take the picture now, and take the picture with whatever into whatever register is selected by WA if WRF is high, if WRF is a 1, and the data you put in is given on WD. What should we do with those clocks, do you think? Do the easy thing, right? Tie them all together, right? So if there's 10 Phil would hate me for this, right? But if there's 10 SLRs here, you push them all down at the same time. Click, right? But of course, only one of them is turned on, or maybe none of them is turned on. But at most, one of them is turned on. So you go like this, and your finger doesn't work on 9 out of 10 of them, but the 10th one actually takes the picture. So what you do is you hook the clock in parallel up to each and every one of the inputs. And in general, this is the architecture that's used to build that register file. And that's all there is to it. It's really simple, okay? And each of these units is exactly the same kind of device we talked about in the last few classes, and the same sort of device that's going to be used to hold the contents of the PC, for instance. A simple 32-bit register.
32 wires comes out of each one of those.
That's absolutely right, yeah. If I wanted to, I could mess this thing up by putting a slash here on each one of the wires here and putting 32 on each one of them. But the truth is that this works no matter how many wires come out of each one. So the architecture is general. In our specific case, yes, you are right. All of the data paths are 32 bits wide. The address path is 5 bits wide, and everything else is 1 bit wide. Yes. Okay. Cool, huh? How to build a register file. Okay. Is it practical to do the big memory this way? So I want to hypothesize that we're going to do 128 megabytes like so. So I'm going to have 128 million 32-bit registers. You know, they're going to reach from the ceiling down to the floor. They're each going to be very thin, right? 128 million of them stacked up. And then I'm going to have a giant decoder over here on the right that's going to choose bzzz, which one I'm going to look at. And a giant, this would be a giant selector choosing which one I want to read. And a giant decoder on the other side choosing which one I want to write. And these two big arms would kind of, you know, go back and forth saying, I want to read word number so-and-so. And they choose one out of 128 million or even more, 4 billion, you know. Lots and lots of thin. Do you think that we're going to build it like that? That's crazy, right? This architecture that we have before, let me actually go back to this. This is fast, okay? It turns out this is a small, fast memory. But if we want to do a big memory, and we try to do it like that, it would be ridiculously slow. Like even slower than the RAM actually is inside of your PC, because the selectors would have so many inputs. The fan-in would be so great that the amount of electrical charge you would need to get data through this monstrous thing would be so large that it would take forever for that charge to build up to get the data out. Okay?
How big can that register file get?
That's a great question. I would say probably going beyond 1,000 registers is starting to push it. Okay? So on the order of 1,000. 1 million is way too high. Okay? 1 billion, which is what we're getting close to now in terms of RAM these days, much, much too high.
Each register is
So-
4 bytes.
Where each one of these registers is 32 bits, yeah. But there actually have been machines, and I was involved in the design of one, where there are thousands of registers in the register file. So, and it turns out that there's an advantage for doing that for certain things. Okay, so how do you build a big memory without making it so slow that it's not worth using at all? Well, first of all, you say to yourself, instead of this one-dimensional structure that I just showed you before, which was a stack of registers from the floor to the ceiling, let's at least have a two-dimensional structure. Because after all, chips, the integrated circuits that things are made out of, are two-dimensional in the first place. So let's lay out the bits like this, rather than just in a straight line, and at least get the square of whatever the sizes of the edges are. So if there are n squared bits inside of this picture here, we only need a structure that's n by n in order to generate them. Okay? And what we're going to do is we're going to store 1 bit at each one of these intersections. Now you say to me, but you want 32-bit words. Well, that's easy. I just have 32 of these chips, and I can do the job. Or you can think of this as a 3D stack that has 32 levels like this in it, that being the 32 bits. And each one of those levels has X and Y in order to choose which bit that you want. Okay? And modern RAMs, or random access memories, are built like this, where we use the nice fact that 2D allows us to take the square root of the number of bits that we're trying to do. Okay, so for instance, a megabyte would be, so let's say we had 1 meg. We wanted to build a 1 meg chip, right? 1 meg is 2 to the what? 2 to the 20, okay? Because 2 to the 10 equals 1024 equals 1, quote unquote, k, okay? And so 2 to the 20 is 1 meg. 1 meg of anything, okay? And so what we're going to do to this thing is we're going to split it up into 2 halves, being a set of bits that's going to be 10 bits wide, like this, 20 bits wide because 2 to the 20, draw this like that, and another set of bits that's 10 bits wide. And so this will then go to a structure which is square, and we'll have 10 bits here, 10 bits here, so we'll have 1,024 rows and 1,024 columns. And that's reasonable to build. Okay? So, that's how we're going to build big, slow RAMs. And then the question is, what are we going to do inside of each one of the cells? Because even though we're in 2D, if we have millions of cells, it's important that the amount of storage that we have there, the circuitry we devote to storing a bit there, is as minimum as possible. Because if it's not, then it's going to drastically cut down on the amount of storage that we can have. And so what I'm going to do now is I'm going to go a little bit into physics. And again, if you don't quite get this because you haven't had it before, it's okay. Yeah?
We're using selectors on each axis there.
Let me make that a little more clear. I think on the previous one, I used a square at the bottom, which wasn't quite so nice. Here's what I'm going to do. I'm going to use a decoder over here. Okay, I'm not drawing this quite right here. Let me draw this right. 10 bits go in here, and I have a 1, 2, I'm going to put a logic 1 in there, and that's going to choose one of the rows. Okay? And then all of the columns are going to come down like this. And what I'll do is I will have a selector down at the bottom. And I'll take my 10 bits and I'll put those into there. And that will choose one of the 1,000 different columns, and out will pop the bit that I want. The bit that I love, okay? So these 10 bits will be used to choose the row. And once we energize the row, the 1,000 bits that are on that row will come down, and then we'll choose which column we want, and that'll get us 1 bit. And there are 2 to the 10th times 2 to the 10th or 2 to the 20th different possibilities of choosing a particular bit out of this matrix here. And if I take this and replicate it 32 times like so, and have all of them do the same thing, they're all going to kind of go up like this, and they're all going to go across like this in step with each other. Whichever particular place in X and Y I choose here will be the same place along all 32 planes, then I'll get 32 bits out of storage from this 1 mega word system that I have.
What does the 1 correspond to there on the left side of your
The
screen?
1 says this is the one that I'm going to choose. So this is a 1, and all the other ones are going to be 0. If you
So
remember,
it's not a wire coming in with a value 1.
it actually is. It is a constant 1. If it was a voltage, I would say I pull this voltage up to a positive voltage all of the time. It's the constant 1.
Okay, so that's like a read enable.
Exactly. Okay, but we'll talk about exactly what this thing does. And this is going to be a little bit of a hint into the circuitry that's going to be involved into storing each one of these bits. Okay, yeah.
The 10th value, or 2 to the 16th, in our case, value selector is not prohibitive.
2 to the 16th is getting there, but it's not that bad. Okay, 2 to the 16th is a little bit bigger than what we can do now. But what is the largest size of a DRAM chip now? 16 or 32 megabits, or 64 megabits, or 128? So it's getting up there. Okay, it's not quite at 4 gigabits, but it's getting towards there. And so in another 5 or 10 years,
Why don't you choose
it'll be
16?
16.
That's how many memory.
Because we have 2 to the 32 different places that we can access. So if I wanted to implement the entire big slow memory with 32 of these planes, each one would have to be 2 to the 16th by 2 to the 16th large. Okay? Now, we're going to learn in the last third of the course that we're not actually going to do that. In other words, the computer will be set up so we could fill it up with that much RAM, but we're actually going to fill it up with less. And we're
In
going
this
to
case,
show,
we'd have a series of chips that would each pull out a couple bits to
right,
get our 32-bit total.
we could do that, or we could actually leave big holes, and I'll show you a way of faking the fact that we don't actually have all the RAM that we thought we had. Okay, but that's towards the end of the course, so let's not do that now. Okay, but in general, what I wanted to show was that using a two-dimensional structure, it makes it easier to store lots of bits. But that's only one step, is the geometry. The second step is, how do I actually store a bit in one of these places here? Okay. So let's talk about that. The way that we're going to do it is with two devices, and I alluded to one of them yesterday when we had fun talking about how to build a light switch that you can work at the bottom and the top of the stairs. So the first element we're going to use is a switch, just like the light switch you have in your home. And the second element that we're going to use is going to be something called a capacitor. Now, how many people here have not heard of that and don't know what one is? And it's okay. You don't need to be ashamed. A capacitor. Okay, what a capacitor is something very similar to the symbol that it has, which is a device that has kind of two plates. Okay, two plates of metal that are separated by an insulator. And the characteristic that a capacitor has is that it can store charge. So if I send electrons down this wire, they gather on this plate here, and they can't jump across the gap because there's an insulator. So they just kind of all hang out here and get stored. It's like a bag full of charge. Okay? And what's really great about it is that if I close this switch and I send a bunch of electrons to get stored in the bag here, I later on can close the switch again and I can pull them out and I can find out whether or not they were there. Okay, so think of this as like a little bathtub, right? I'm going to close the switch and maybe send some water in and fill up the bathtub. Okay, that's how I'm going to do it right. And if I fill up the bathtub, it'll be a 1. If I close the switch and I don't fill up the bathtub, it'll be a 0. Okay, those are the two states that I'm going to have. And then I'm going to open the switch. And bathtubs, if you live in a new house, don't leak. And the water stays in the tub. Okay? If you live in a nice old house in this town, and you stop the drain with one of those little things, right? What happens? An hour later, all the water's gone. Why? Because it slowly dripped by all the leaks that there were in the stopper. And in fact, the capacitors that these memories are made out of work exactly the same way. The insulation is not perfect, and it leaks. It doesn't leak so bad that you can't store anything there at all, but it leaks bad enough that after a thousandth of a second, get this, a millisecond, you can still trust that the water's there, but much past that, you can't trust it. Okay? And the guarantee that they give, usually with these chips, is that the storage on these little plates, which serve as little bathtubs to hold charge, is leak-free on the order of a thousandth of a second. Just like, you know, if you fill up your tub, even if it's a leaky tub, and you come back a second later, it's not that all the water is going to be gone, right? It takes, you know, an hour for the water to slowly leak down. So with these typical devices, it's on the order of a millisecond, the time constant, but you can depend that the charge will still be there. Okay, and we'll talk about what that means. But here's how it works. The row wire, okay, this is actually called RAS, row address select, is going to be used to close the switch and to let water from the column either into here or out of here, to either fill up the tub or to drain the tub. And then the switch will be opened because the row address selector will be turned to 0. The switch will be opened, and then we're going to hold on to that stuff. So in the time between when we write it, which was when the switch was closed, and when we're going to use it in the future, we're going to leave the switch open because we're going to be busy writing other things in here. And we don't want to sort of screw this one up. Then sometime in the future, we'll want to read it. We'll close this switch again, and then we'll sort of suck all of the charge out of here, and we'll measure how much we got. Okay, that's the way that you do it. You take a pail, you fill up the bathtub, you take all the water in the bathtub, you put it in the pail, and you hold the pail up to the light. Did I get water or didn't I get water? Okay? That's actually how it works. But if too much time has passed, you're dead. Okay? And that's the reason that if I suddenly disconnect the power from my laptop and hook the power back up, that the laptop doesn't come back to life exactly where it left off, unless I write a bunch of special software to take everything in the memory and write it out to non-volatile storage, which is the disk, which stores things a totally different way. I can't trust the DRAM, the dynamic RAM, in the machine to hold on to this charge. And in fact, this is called DRAM, the D of dynamic random access memory. The D means that it is dynamic, meaning that I cannot depend on it statically to hold charge. Now, how do I actually deal with the fact that it's leaking all the time? What if I actually wanted to use my bathtub as storage? Well, what I'd do is that every minute or so, I'd go in there, and I'd look down there and look at the water, okay? And I'd say, well, is the water low or high? Well, it's probably not all the way high because it's leaked out a little bit, but it's probably more than half high, right? So if the water's more than half high, I'll open the faucet, and I'll fill it up all the way to the brim, and then I'll turn the faucet off again. Then I'll go away for a minute, and I'll come back a minute later, and I'll look again. Is it more than half high? Well, yeah, okay, I'll fill it up to the brim, turn it off. So I will refresh the storage in the bathtub by reading it, checking to see whether it's a 1 or a 0, is it high or is it low, and writing it back. And the key is that when I write it back, I will write it back with better quality than I was willing to accept when I read it. When I read it, I was willing to accept it as a 1 if it was more than half high. When I write it, I will write it with better quality in that I will fill it up all the way to guard against the fact that it may leak down a little bit. So typically the charge inside of one of these capacitors, if it's being maintained at a high, kind of looks like this. So here's where we fill it up to, and then it leaks down. Fill it up, it leaks down. And here's the threshold that we use to determine is it a 1 or a 0. Now, if we're lazy, this will leak down past the threshold, and we won't know whether it was a 1 or a 0. But if every so often we go over to that thing and say, oh, let me check to see whether you're high or low, and then I'll write back with higher quality than I was willing to accept when I read, and you write back, this is a nice, strong, high voltage, then I'm okay. And it turns out that every computer, including this laptop here, checks this thing of every bit in the entire system every millisecond, every thousandth of a second. Every bit in the system is being read, restored, in other words, checked whether it's high or low, and being restored back, written back at a higher value. Okay? So that's a pretty cool thing. And it turns out that there are special mechanisms inside of the circuits themselves, so the microprocessor doesn't have to go through and read all the millions of bits that there are out there. It can actually send a signal to the chip which can massively, en masse, take a whole row of these bits, read them, don't do this thing of choosing one of them, restore them all, and write them all back. So it writes back, in this case, 1,000 at a time. It reads 1,000, restores 1,000, and writes back 1,000. And so all you need to make sure is that you go around and around here at least one circle every thousandth of a second, which is actually pretty easy to do. And in fact, there are even some chips now where all the logic for doing that is built into the memory circuit. And from the external world, you can't see that go on at all. Except on the inside, it's going around and around and around, checking the bathtubs, filling them up, checking them, filling them up, all the time. And that's, in fact, what's going on inside the chips on the inside of that thing, which is a pretty cool thing. So, minimum circuitry. What's that?
What's that type of RAM?
Oh, geez. I think it may be called hidden refresh or automatic refresh, or on-chip refresh.
Still SD-RAM.
It is still DRAM. The S of SDRAM, S is for synchronous, and that refers to some fancier circuits, which we're actually going to go into, that talk about a slightly different structure for here. Okay? Turns out that instead of doing this, which only grabs 1 bit at a time, if you want 1,000 bits, you can get out the 1,000 much faster by doing one transfer, and then in assembly line fashion, like we talked about the last time, you get zip, you get them all out. And so that's why SDRAM is so much faster than plain DRAM, which is the way that this thing works. But for now, let's just talk about DRAM. And for now, the key is to understand that at minimum, what storage is in a computer is some kind of device to store charge. Okay? And pretty soon, I'm going to get into physics with you, and I'm going to tell you it's not even the charge that is the fundamental thing, it's energy. Okay, and don't worry, this isn't going to turn into some new age course, okay? This is real energy. This is like, physics, E squared, E energy, right? Okay? And so in the bathtub, what's the potential energy of the water sitting in the bathtub? Or actually, if you want to get really fancy, it's the negative of the entropy of the fact that the water is in the tub and not out on the floor. Okay? So the maximum amount of randomness that can happen when you have kids like me, this happens quite often. There's water all over the place, right? Okay, and the water's neither both in the bathtub and outside, and you really can't tell. What this thing is doing is saying by specifically placing electric charge on this plate on the top, okay, we're basically storing some energy. Those of you who had physics know that the amount of energy stored on a plate like that is 1/2 CV squared, where C is the amount of capacitance, V is the voltage, and it's 1/2 CV squared. The formula doesn't actually matter. What does make a difference is that what we're detecting is whether there's energy stored on this plate here. And the way that we're going to do it is we're going to close the plate, and if we want to write a 1, we'll pump energy in. If we want to write a 0, we'll suck any energy that might be there out. And we'll make sure that that's out. And we're actually going to pump it in and out on this wire here, and we're going to choose whether or not to do it on this wire here. And if we want to read whether or not there's a 0 or a 1, it turns out that reading that is a destructive thing. In other words, we're going to close this switch, and we're going to suck all the energy out that we can, and we're going to measure how much we got. And in the process of doing that, we will have erased the bit. But that's okay, because we remembered what it was, and after all, we have to write it back anyway. So then we'll restore it to either a lot of energy or no energy, and we'll go whoosh and write it back here. So every time we read a bit from something like this, we actually write it back also. And furthermore, every thousandth of a second, if we haven't done it, we read and write just to keep it refreshed and up to date and either high or low.
Two questions for you. The first is, I don't know that much about electricity, but I'm thinking about the electricity flowing out as water would flow in a river. And if water's flowing from farther away, the level of the water is going to be more dissipated.
Absolutely right.
The longer it flows. So if the electricity were to flow like that, we would have to have a higher original voltage to get our minimum half voltage if we're going twice the distance, for example.
I totally get what you're saying. You're worried that the wires here may be thin and long, like a river, kind of going a long distance, and it's not a very wide river. And so if we put a lot of energy in here, that it may, have some resistance before it gets to the junction, right? That's absolutely right. And the designers of these chips take great pains to figure out, if I put a high voltage here, what's it look like here? And it turns out that it changes how fast it takes for the high voltage to get to this place. And we're going to talk about that. And what limits the speed of the memory is just what you're saying, like the time it takes for the water to get down the river from one place to the other, the resistance of the wires, the capacitance, which is kind of the size of the river on the way to the final place, to the bathtub here at the end, will limit how long it takes to fill this thing up. Okay, and that's the fundamental limit to speed on the thing. We are going to talk about all of that stuff too.
Secondly, what are the switches?
Funny you should ask.
Transistors or-
Oh, shoot. Okay. Well, all right. We are going to get to it. It isn't the next slide. It wasn't the perfect question, but nearly the perfect question. Okay. Let's talk about how we tell whether or not the bit is a 0 or a 1. It turns out that because of just the effect that you mentioned, that when we drain the bathtub here, it's going to go down this pipe, okay? By the time the water gets down to here, it's extremely difficult to tell whether there was any water in the tub at all, because in fact this tub is a thimble. And in fact the capacitor that's here, the bathtub that's here, is the thing that takes up the space. And of course, if you want to pack the most number of bathtubs into a given space, You want the tubs to be as small as possible, right? But what happens when the tubs get really, really tiny, a little thimble for each one? Then when you say, okay, you there, let me suck on my straw. Did I get water or didn't I get water? Well, if the thimble is this big and it gets tiny and tiny and tiny till it's just a drop, did you get a drop or didn't you get a drop? It becomes tough to tell. So there's a trade-off of how large the cell is here and how difficult it is to sense whether it was a full or an empty tub. And so there are these very specialized amplifiers called sense amplifiers, which you see in the picture right there, that are used after you select the row and you connect the capacitor associated with that row and the column up to the column, and the straw sucks all the charge down to be able to sense the difference in the charge. And it can be on the order of microvolts of difference by the time it gets down here, just the question that you asked, to sense whether or not it was a high or a low. And these amplifiers really can tell the difference between one or the other.
Does the amplifier know the address from which it was coming to and
No.
amplify by a different amount? By
That's
saying,
an excellent
oh,
question.
well, that guy was farther away, so he needs to be boosted by a greater amount?
That's absolutely right, and the answer is yes. Okay, so they actually do that. They actually know that there's a scaling law between what happens down here and what happens way up here. In fact, they usually have two sets of amplifiers. They have one down here and they have one up here. This one gets it from this half of the chip down. This one gets it from this half of the chip up. There's all kinds of other tricks. Sometimes the distance is too far. They break the chip up into 4 halves. They have amplifiers here, 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 and here, in lots of different places. There's all sorts of tricks that they
That
do
allows all the capacitors to be the same size.
to try to act to be the same size, yes. Yeah. It is a hard thing to do. Sometimes, in fact, in the old days, this problem was so hard that they wasted half of the lines, and whenever they had high charge in one, they'd put low charge in the other. They'd suck down on both of them and look for the difference. So whatever effect happened to one would happen on the other. You throw away half the bits, but you sense what the difference was between one and the other. One of the things that they do now is that they have what's called a dummy column, like this, that they always fill up, okay? And another one that they always set to 0, okay? And when they choose any column, they suck down from here too, and they look at where the one that you're checking falls with respect to the references here on the end, which are always full or always empty. And so that's another way to calibrate it.
Besides capacitors?
That's really a great question, and it really is. There have been a zillion different ways. A lot of them use magnetism of one form or the other. And you try to, in the old days, of course, there was core memory. And so you had wires that crossed, and when you put a current through a wire, you get a magnetic field that goes around the wire. And you can have a ferrite core, and you can magnetize it either one way or the other way. And then you can send another wire through and tell whether or not it was set one way or set the other way. So that's been done. There have been many different ways that have been tried, but so far this still seems to be the best way that is actually known. They all have in common, however, that there's energy that is stored. In fact, it turns out that you cannot store information without storing energy. Okay, that's the key element in physics. That in order to tell information, basically you have to store energy. In order to transmit information from one place to the other, you need to transfer some energy from one place to the other. And we'll talk about what that means and what you do with the energy once it's sent from me to you if I'm sending something. When I'm talking to you, I'm making the air move. And lo and behold, the air moves and it moves towards you, and that is energy. There's actually real power in microwatts going from my mouth to your ears. And your ears shake. Okay? And if this room had perfect flat walls, the energy would have nowhere to go, and it would keep bouncing around and around and around like echoes, and pretty soon the whole room would fill up with echoes, and we wouldn't be able to hear each other. But luckily, you're all wearing these soft clothes, so when I send the energy to you, pretty soon it gets dissipated as heat within all those clothes. So it's all hot air, right? So but anyway, you'll find as we go on that energy is the key to this whole thing.
I
Yeah.
can't remember why a capacitor works. Why isn't it just like a permanently open switch?
Right. Well, actually, an open switch is also the same thing like that, too. But what goes on is that you know that a electron, okay, that negative and positive charges kind of like each other, right? And there's a force that makes them want to go towards each other, okay? So let's say over here I have an equal number of negative and positive charges that are hanging out, okay? And the same thing here. plus, minus, plus, minus, plus, minus. Well, now I go and I dump a bunch of negative charge here. Okay? And actually, whenever I dump charge in to complete the circuit, I actually have to pull some out of here. So some negative charges are going to be sucked out of here. So that's what it actually means to put charge into a circuit. Well, what will result is an imbalance. I'll have more negatives. I'll leave a few of the positives in here. But most of these, not even most, but there'll be more negatives here than there are positives. And down at the bottom, there are more positives than there are negatives. And I'm grossly overdrawing how many there are. Okay? Usually the shift is very, very small, 1 part in 10 to the 20th or something. Okay? Very, very slight shift, even for pretty big voltages. Okay? Now I open the circuit. So this thing is just standing by itself. Why does this thing stay like that? Well, the first answer is that there's nowhere for these guys to go because the circuit's open. But the other is that the negatives here want to get to the positives, and the positives want to get to the negatives. So these guys, seeing these guys a short distance, try very hard to get towards each other. So there's a force that pulls them towards here. And these guys try to get towards here, so there's a force that pulls them towards here. And so you get these forces that are blocked by the fact that there's an insulator here. If you were to short this out, you get a nice spark, and they'd all find each other. But they don't. And so you can now measure the voltage here, and you'll find that this is negative and this is positive. And there's an actual voltage on this thing. And I can take this and I can put it in a piece of glass, which is an insulator, and I can walk around all day with it, and it'll hold the charge. And then I can come back and then measure the voltage again, or I can suck all the charge out of it by connecting the two ends, okay, or maybe dumping the charge into some other circuit, which is that sense amplifier, and seeing whether or not there was charge. Or I could polarize it the other way, put the positives here and the negatives here. But anyway, that's how it basically works. They're trying to get to each other over the plates.
Yeah,
Yeah.
the mechanical dual is a spring. So it's like
That's absolutely right, yeah.
compress the spring and store the energy. in it.
Absolutely right, absolutely right. So I could have a spring and squeeze it and then hold it, or I could have a bottle of air and pressurize it, right, and then cork the top and walk around the bottle of air. And that could be a 1, and a depressurized bottle of air could be a 0. In both cases, though, in all the cases, in every case there could possibly be, I must do work to create the energy that's stored in this thing. And then I can run around and have it, and then I can let the energy go and tell whether or not there was energy there. So that's kind of the key element in all this stuff.
How do you put, with the insulator there,
Yeah?
how do you put the charge in?
So that's why you need the switch. And we're going to talk about how to build that. And
There's still the insulator between the road, between the charge.
oh, sure, but there are two paths here, right? I don't need to short this out by shorting these two. I can also pull the negative charges out of here and bring them back around to the other side if I close the switch and neutralize it that way. Okay? Good. This is fun. Boy, we should just teach physics. You know, we should kind of bag all the rest of this stuff and just do physics, because physics is really the real science, right? All this stuff is sort of flaky stuff. So. Pseudo-physics. Okay. Read-only memory is just like a random access memory, except that you can never write any of the values. They're stuck at 1 or 0. Inside of that the beautiful old Commodore 64 that's over there, which I used to play with too when I was a kid, are memory cartridges called ROMs, okay? And they work like this. Structure's a little bit different. The row selects a switch, okay? And that chooses this path here. And this path is not a capacitor, but is in fact another switch, which goes to ground. Okay, ground is the symbol here. Okay, and basically what it does is if this capacitor here, which is floating out in space, has charge on it, has energy in it, this switch will be closed forever. And if this switch closes and this switch is closed, then this wire will be connected to ground. And there's a sense circuit down at the bottom that tries to put a little bit of current in and see whether or not it's hooked to ground. If it is, the current flows. If it's not hooked to ground, if it's an open circuit, the current doesn't flow. Okay? Now, the capacitor here is charged forever. Okay? It's, in fact, 2 pieces of semiconductor inside of glass. of silicon dioxide. Totally isolated, okay? So there's a piece of semiconductor which can conduct electricity a little bit, and another piece like this down at the bottom. And this piece is totally enclosed in 3D in glass. It's actually grown on the circuit like that. And it either has charge or it doesn't have charge. And glass is an excellent, excellent insulator. In fact, it's so pure here that this charge will last for 20 years. That's how good the bathtub is. And why is this bathtub so good? Because it doesn't have a drain. Okay, there's no way to get the charge on and off of here. That's how a ROM works. Okay, and why a ROM, the cartridge you plug into your Game Boy, right? How the heck does that thing hold on to what it knows? Well, it turns out that there's two kinds. One's called a mask ROM, where they actually manufacture it. Some of them will have the switch closed, and some of them will just have the switch open. But the more common one is this thing called a EEPROM, Erasable Programmable Read-Only Memory. And it works like this. The capacitor is like this, except that there's no switch hooked up to here. Okay, this store, and because there's no switch, the switch can't leak. And because it doesn't leak, you don't need to refresh it. And the charge lasts for 20 years, and even more in the case of that thing, at least 20 years. If you get it real hot, it lasts for less. So how do you store energy in here to begin with? Well, it turns out the glass is an amazing thing. It has a characteristic of two things. First of all, you put another plate on here of semiconductor. So this is really 3 plates, like so. And even though there's glass here, if you put enough voltage on this guy, like 20 volts, most of these things run at 5 volts, but if you put 20 volts, due to a process in physics called tunneling, some of the electrons here are so hot to get to the other side that they will squirm their way through the insulator and get to it anyway. Okay? But you need a lot of volts here. And ordinarily, when you walk around with a chip like that, you don't have 20 volts to get to the other side. So the chip will last for 20 years if you don't put high voltage on it. But if you put this EEPROM inside of a EEPROM programmer, which has 20 volts on it, it can still read or write, store or take away charge from this guy in the middle. And as soon as you take away the 20 volts, it lasts forever. Okay? The guy who thought of this was a wonderful guy. I think he was at Bell Labs. And no one believed him that he could do it. And he actually could. Anyway, that's one way to do it. And it turns out that another way to do it is if you shine ultraviolet light through here. The ultraviolet light excites the atoms in the glass, and they turn a little bit into a conductor, and the charge leaks off. So it makes the glass not quite so good.
Is that
And
only
so-
while the ultraviolet light is...
Only while the ultraviolet light is on. So in general, these chips can be erased with an ultraviolet light, and you see some of them with a window on the top that has glass, right? If you shine a really strong ultraviolet light of a certain wavelength, and there are certain wavelengths work better than others, depending on how the glass is made, it'll allow all the charge to leak off, and you'll basically clear the ROM. And then you can program it by setting certain of these plates to a high voltage, and it'll allow the charge to sneak on to certain ones. And that's how it's done. Okay, so if you ever see these chips being made, you'll actually know how the thing works. And you'll think about bathtubs, right? So
now do those switches that are on...
there's some high voltage now trying to get through. See if it'll tunnel through, you know? I'm sorry.
Do those do those switches ever change? It sounds like you're saying that it's the orientation of the switches that determine the memory, because
That's absolutely right.
capacitor's always set.
Right. Right. So if the capacitor here is high, the switch is closed, and if the capacitor is low, then the switch is open. And what is the switch? Here's the switch. Here's the answer to your first question. That excellent question you asked. What is a switch? The switch is this thing called a field effect transistor. Okay, and we're going to talk a little bit about how this works, but we won't get too deep. And this device on the left, which I've drawn as a switch, which is controlled by a wire here, which allows the switch to turn on and off, is in fact this device right over here, which is a gate. That's what this thing is called here. And this thing, one is called the source and the other one is called the drain. And the idea is that electric current is trying to get through this thing and this is a gate that says whether or not it gets to go. In the same way that this is a switch, the electric current is trying to get through this path here, and whether or not the switch is closed depends on whether the gate is high or low. And that's how these things work. Now let me draw you, I don't know.
How does the diagram on the right work?
Okay, so let me actually draw that out a little bit. And we're going to be doing quite a bit of this. And I'll use color, but I'll make it clear also, okay? It turns out that when you're building semiconductors, you can build them in two types. You can build them as negative charge or as positive charged ones. One is called N-type and the other one is called P-type. And so what I'm going to do here in orange, I'm going to draw it like this, is I'm going to say that this is P-type semiconductor. It's also, you just put a P there. And what that means is that inside of here there are positive charges that are free to move around. Okay, free to go back and forth. And I'm also going to draw another type over here. And I'll draw it like this. I'll draw it over here as well. And these two here are going to be N-type. And in this kind of material, there are going to be some free negative charges that can go back and forth. And I'm going to be explaining this more and more as the term goes on. But in general, if you want to pass current from this end to this end over here, it turns out that it won't go. Okay? In general, if we didn't have this thing on the right, if we just had some N-type over here and some P-type here, and they had a junction in the middle, and we tried to pass current one way through that junction, it would allow the current to go one way, but it would not allow it to go the other way. And we don't have time here to explain exactly how, but what's called a PN junction, or a NP junction, here's N and here's P, is what forms what's called in electronics a diode, which is often drawn like this. In other words, a valve that only allows current to flow through one way. And if you'll notice, the structure over here is such that there's two diodes, each pointing towards each other, like this, towards the middle. And so if I've tried to pass current through this way, it'll get through this one, but it won't get through that one. And if I try to pass current through the other way, it'll get through this one, but it won't get through that one. So this NPN structure, and you could also build it PNP, it doesn't actually make any difference, is a structure that does not let current go through. It functions as an insulator, an open switch to current. Okay. But guess what? You can make the switch close. And here's how you do it. First of all, you cover the whole thing with a layer of silicon dioxide, which is glass. A beautiful insulator. So this is SiO2. Glass. Perfect insulator. Okay? And then on top, you put another piece of semiconductor, which is made out of polycrystalline silicon, but it actually could be metal. Anything that is a conductor. Doesn't matter. And you hook this up, and this becomes what's called the gate. And guess what happens? In the same way the capacitor worked, if I put a lot of positive charges into here, let's say I fill this up with positive charge, guess what gets attracted to here, to the surface right over here? Because remember, positive and negative want to go towards each other. Guess what gets? It turns out that there's a few negative charges floating around in here. Not many, but there's a few. P-type means there's a lot of pluses and a few minuses. But if I put positive charge on the gate, all the minuses drift up to the top because they all want to get close to this positive gate. And so what you get here, and this is just an amazing thing, is you get a very thin layer, once this gate becomes positive, of sort of mirror charges on the other side that are negative. They all get attracted to this point. And this material, which was originally p-type throughout, because you put positive charge up here, gets a thin layer on the top, sort of like water on ice, where it actually switches to be n-type, because so many of the negative charges have been attracted to the surface. And look what just happened. Suddenly, I have a clear path across this NPN junction. That's all n-type. And n-type works just fine. And it's a closed switch. So I can make this switch go on and off by charging this gate up. I charge the gate up, the ends come up, the switch will close. I discharge the gate, the ends go back down and mix up, switch is open. And this device here is called a field effect transistor. This is basically as deep as we're going to go into semiconductor physics to talk about how this thing works. And the symbol for it is that. Okay, where that exactly corresponds to the 3 terminals that I've drawn here. We're trying to get current through this path here, and it's controlled by this gate. And notice the space between the gate and the channel that we're trying to get the charge through. And that space is where the insulator is, and that's to indicate that I charge and discharge there, but this gate doesn't really physically interact with any of the circuit down here. It only opens and closes the gate. Just like a person that opens and closes the gate but doesn't interact with the people that flow through. Okay?
How large a charge would you have to have?
You can have, let me get it exactly right. It's in picocoulombs, so of that order. Very, very small. And the devices here are fractions of a micron on a side. Okay, that's how tiny they are. Very, very small.
What did you say the material of the p-type and n-type?
These are both silicon, Si, except that they're doped a little bit. So silicon by itself is neither N nor P.
Okay.
And if you add a dopant to it, you can switch it from one to the other. Okay. And so arsenic is a dopant. There's a phosphorus, gallium, thanks. And so you can change it from one to the other. But anyway, there's a whole bunch that you could learn about that, but there's no way I can teach architecture in 3 weeks and also do this stuff. So, okay, but this is basically the field effect transistor, and it's what we're going to use for this switch. Alrighty. The switch is going to work like this. If we put a high voltage over here, we get a short circuit. If we put a low voltage over here, we get an open circuit. Now, it turns out that there's an exact dual to this where you switch around the P's and the N's, and if you think about it, what's necessary in order to close the gate, where it was a positive charge in this case, is actually a negative charge in the other case. And so we can, in fact, build the complement devices. And the way we show that is with a little bubble over here, which is the sort of logic drawing symbol for an inverse. And this is called a P-channel FET as opposed to an N-channel FET. And as opposed to the other one, which was closed when the input was high, this one will be closed when the input is low. So the circuit will be one that has the opposite action with respect to the gate. Gate is low, switch is closed, gate is high, switch is open. And this is basically as deep as we're going to get, and then everything else we're going to build out of these parts. Okay? All right, onward. How do we implement multiple ports in this kind of memory system? Well, we need 2 read ports and 1 write port. But actually, we don't really need to do something as complicated as that. What we really need is 1 port that can do either reading or writing, and another port that does reading. And the reason for that is that loads and stores do not happen at the same time. With the register file, this is the big, slow memory. The register file, we were reading from 2 places and writing to a 3rd one all at the same time. But remember, the interactions with the memory are serialized by the fact that the big memory is accessed for only 2 reasons. One is to get what the PC points to and fetch the opcode. That's what you need the read port for. The other is to do load and store, which is what you need the other port, which sometimes does a read and sometimes does a write. Furthermore, we notice that load and store don't really happen that often. The whole idea of our machine is that we're going to do most of our work with the register file, and only once in a while we're going to do load and store. So what that means is that most of the time we don't even need this second read-write port into the system. And so what we're going to do for now, and we'll talk about how to perhaps improve the system afterwards, is we're only going to use one port. We're only going to use a one-port memory. And that one port is going to be to read what the PC points to. What is the instruction that we want to do? And if it ever happens that we need to do a load and a store, what we're going to do, instead of trying to build a memory with 2 ports on it, or God forbid 3 ports on it, and have the expense of these 3 expensive ports all the time, when we're really only using one most of the time, is if we ever need to do a load and store, we're going to hiccup. We're going to say, well, wait a minute. We're trying to do a load or a store. Don't fetch a new instruction to do. Instead, stall. And wait for the next cycle and insert an extra hiccup. And during that middle cycle of stall, use the one port that we used to use for doing reads and use it to execute the load or the store. In other words, we're only going to have a single read-write port to the main memory. Most of the time it's going to be used for doing reads, for reading the instruction to be done. Occasionally when the instruction is a load or a store, after the instruction to read, after we do the read to find out what the instruction is, we'll stop, we'll do the load or the store in an extra cycle, and then we'll pick up from where we left off. Okay? So the answer to this question is we will not implement multiple ports in the big memory because it's just too hard. We'll just have a single port. And in general, this is true because you saw the amount of hair we had to go to with the register file, right? With thousands of wires and an extra circuit on the right and maybe 2 circuits that mimicked each other. It's just too hard to do. So the question is, if we wanted to stall this machine, and I'm only going to hint at this at the beginning and then we'll talk about actually doing it afterwards, what could we do? Let's say we just read an instruction and it turned out that it was a load or a store. And we don't want to do the next instruction. Instead, we want to stall this machine and we want to say in the next instruction, do not proceed. Spend that time finishing the load or the store by using the same port on the memory that you used before. How could I stall this thing? And this will turn out to be a key for everything in the future. What do I need to do for an instruction to make it not happen? So what I mean by stall is I effectively kind of disable the machine and it just sits there and stalls for a while. Stall, 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 stall. Then I can turn it back on again and it picks up from where it left off without anything going wrong. What wires can I affect here to cause a stall to happen? It's an amazingly simple answer. All I need to do really is, I need to disable write-enable to memory. I need to disable WRF. And what else? I need to be careful about this. And I didn't show an E on the PC here, but I need to add an E to the PC saying don't update the PC. Now if I say don't update this, don't update this, don't update this, it becomes the question if a tree falls in the forest and no one's there to hear it, does it matter? Right? Or did it fall? Okay. The fact that this is computing the most profound thing in the universe will make no difference if we disable the writes on the registers down at the bottom because we're not storing the answer. So it's very easy to make this machine hiccup and do nothing and stall it for a certain length of time by disabling the writes down at the bottom. So in general, we're going to disable WRF, disable the memory write, and disable the PC write when we want to build a mechanism to stall the memory. And I believe in a problem set, you're going to be showing how to build a memory that looks like it has multiple ports for loads and stores, but really what it's going to do is when it's called on to use one of those other ports, it's going to stall the machine, take away the port from where it was just used and give it to the other part, and then let the data go through. And then take a little bit of time to effectively multiplex the use of one port amongst 3 possible sites. So architecturally, everything looks like it has multiple ports, but in fact, we're going to fake the fact that there's 1, 2, 3 ports here by having this be the one that's used most of the time. And if we ever need to use this one or that one, we'll sort of stall the machine and finish up our work on the other 2 and then pick up from where we left off. because it's a big memory, and we don't do this very often, and we don't do this very often. Those are loads and stores. Okay. How to make memory faster, okay? The simple thing is to make the memory really wide. Use wider words. So even if you have a 32-bit machine, if you have a memory that is 64 bits wide, every time you do an execution to fetch some stuff from the memory system, you get more bits. And then those are good for 2 cycles as opposed to 1. But it depends on the fact that if I fetch 64 bits out of the memory, what I'm really doing is I'm fetching 2 consecutive 32-bit words. And I'm hoping that if I fetch this one, then I'm going to need this one next. And you remember, because of locality, sometimes that's true. Often it's true, but sometimes it's not. And we can get into trouble if we fetch a whole lot of stuff and part of it's not used. Okay, so it works in the long run as long as the 2 words are read per machine cycle, but you have to watch out because the assumption is that the words are next to each other in the address space. You need a place to stash the extra word, and sometimes the extra word is not used. So again, the problem with pulling off, if you go to the Library of Congress and instead of taking out 1 book, you say, I work in law, so I'm going to bring home the whole shelf worth of law books, right? Well, that's fine. You go and you huff and you puff and you bring home the whole shelf of law books, and you find that you only need 3 out of the 12 that you brought home, right? So was it really worth doing that, even though you got to do it all at once as opposed to making 3 trips? It's a trade-off, and you need to decide how wide of a word you actually want to get until it becomes clear that you're taking home things that you don't actually need. And so anyway, that's one of the issues, and that determines how long, how many bits wide the memories are that you tend to see. Okay, I believe that's it for today. Summary, what did we learn? How to implement the registers in the big RAM. Multi-port big memories are not easy, so in fact we're going to fake it out with sequential access with extra logic. Wide access, some sort of a cache, the bookshelf to store the extra words that you bring home, and logic. And in recitation, you're going to go over what you did in lecture today.